Data Structure using C++, Module 5, Session 2. Today we will discuss the process known as heapification and the steps involved in heapification. Before we begin with what is heapification, heapification is a process in which the input given to the heapifier happens to be a non-max tree or non-max heap, to be frank. So the input taken by this system before heapification, it would not be a max heap. The output would be a max heap. So the process of converting a non-max heap into a max heap is known as heapification. So now let's discuss how do you heapify a given binary tree. The steps involved in heapifying a binary tree is, so the first step is you need to visit the last element that has a child. Okay, I repeat, you visit the last element that has a child, the first step. The definitely when that is the case, the element will be definitely at a position which is I is equal to the integer of n by 2, where I determines the position for heapifying, and n determines the number of elements in your heap. Okay, so suppose if we assume that there are 10 number of elements in your heap, then I would automatically become 5. So fifth position onwards you need to heapify. Suppose if there were 16 elements, then 8 is actually the position from where you need to begin with heapification. So that's the process. So what you have to do now, after you look at this position, once you take this position, then the element at that position should be compared with its children. So for example, if we consider 10 as the number of elements present in a heap, I becomes 5. So compare fifth node element with the 10th element. So what is 10th element? 10th element will be its child. So 10 and 5 are compared. So if there is a adjustment to be made, you have to make adjustment. For example, if we assume that the ith value, that is 5, heap of 5, if we assume position is 5, and if that number is having a value lower than its child, then you have to make modification. You have to bring the child node back to the parent node position, so that it will not violate the rule which needs to be used for max heap. Okay, so basically what you will be doing is you will take a position, and that position you compare its left child as well as you compare its right child with. So if you want to make adjustment, we do the adjustment. If not, we will keep it as it is, and this has to be repeated for all this position. So once one position is visited, then you need to go to the position, next position which you will be visiting is I minus 1 the position. Then you go to I minus 2 position till you reach the position 1, where position 1 implies here it is a root node. Visiting position 1 implies you are visiting the root node. Till you arrive at the root node, you have to follow this processes. What is the process? Compare the node with its left child as well as right child. Suppose if the node element or the parent node is having a value lower, then you have to make changes. If not, you have to retain the tree as it is. Now let's see how it works for a particular binary tree. Okay, now let's consider before heapifying, let's assume that the content of A is this. So altogether you have 10 elements, and the elements are 20, 12, 35, 15, 10, 80, 30, 17, 2 and 1. So we can clearly see that this is not a max heap. This figure shown is not a max heap. Why? Because the maximum element for this tree is 80, and this maximum element has to be located at the root position, but it is not happening. Okay, so what we have to do, we have to heapify it. Let's see the steps involved, how this 80 goes to this position, how it occupy the root position, and also along with that, what are the necessary changes which we need to do it at this case. So n is equal to 10 first. So first case, since n is equal to 5, we do this process. Find the position from where you need to compare the parent with its child. So find the last element that has a child. So here you have how many parents with children. This is your first node. has 2 childrens. This is your second node, which has 2 childrens again. Third node, again it is having 2 childrens. This is your fourth node, again this is having 2 childrens, and this is your last node. This has 1 children. Okay, so I is equal to 5 implies here this is your last node with child. So node number position is 5 now. You can mark positions like 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So altogether 10 nodes are there, and the elements are also addressed respectively. So visit the node number 5. So here you are now. Okay, then what you have to do next is you compare the value 1 with the 10. Okay, so the child of this node, you have to compare it with the node value. So parent value is 10 and the child, only one child this has, value is 1. So 10 and 1 you have, so we do not have to do any adjustments. So keep it as it is, and you don't have it. This leaf node, this is a leaf node, this is not having any child node, so stop the process. So no more adjustment is required. Stop the process. You can go back to the next node. So now go to I is equal to 4. Next I becomes I minus 1. So move to the next node. Move to the next node with child. So I is equal to 4 is a parent with children. So this is having 2 children. Now both has to be compared. So when you are in this situation, so first 15 is the value of parent now, and that will be compared with 17. So what you have to do, 15 once gets compared, so 17 has to be moved up and 15 can be brought down. So first always you will compare the parent with the left child. Okay, so left child is having a value higher than the parent, so make adjustment. So 17 reaches this position and 15 comes here. Then the updated parent will be compared with this node. So 17 is compared with 2, and you do not have to do changes. So after this process, the content of the tree would look something like this. So this is the structure. Now 17 is updated here, which was here. So 17 goes here, and 15 is brought down, and no need to modify because 17 is greater than 15 now. Also it is greater than 2. Next we need to visit the node I is equal to 3. I again make I is equal to I minus 1. So now I becomes 3. Now here again you have 2 children's, 80 and 30. So 35 is your value, and 35, when you look at 35 value is lower than 80, so you have to make arrangements. You have to change. So 80 will reach this position and 30 comes. Now again this modified parent will be compared with its right child. Okay, so 80 you have and 30 you have, so you do not have to do any modification. No adjustment is required. So you get this as the structure. This as the structure. Now finally go to I is equal to 2 next. When you are in I is equal to 2, now this parent has to be compared with its children as well as its grandchildren too. You cannot just compare it with its children, as well as it with its grandchildren you have to compare. So now you are down here. 12 is compared with 17 first. So when that is the case, 17 moves up and 12 comes down. So now the updated tree has a value 17 over here and 12 comes here. Now again this node has to be compared with its children. So when you have 12 here after this process, okay, then 12 and 15, when you compare, 15 should reach up. So 12 comes down. So the structure will look like 12. Here you have now 15 and 2 you will compare. So no problem, you don't have a problem, no need to change. Then again you go, now here you would have, after updating you would have 17. So this is the first structure, how it goes down. So one step is shown here, that is 12 comes down, 17 goes up, first thing. Then again compare this two, so 12 comes down, is pulled down, and 15 goes up. Now you don't have a problem. So 15 is greater than 2, no problem, no adjustment. Then again when compared 15 with 17, so 15 is lower than 17, no change. Then again now go to the right subtree. 17 is greater than 10, no problem. 10 is greater than 1, so no issue. So this is a max tree, you do not have to modify. Finally go to the node 1, I is equal to 1. Now again you have to make modifications. Left subtree you check. So when you check the left subtree, you don't have a problem. So it is a max tree. Whereas a right subtree, you have a problem to deal with. This is having a value greater than this. So you have to compare the root with its right subtree now. Okay, so you have to do modification. So 80 goes to this position. Okay, so that structure is shown here. 80 goes to that position, but now the process is not completed because 20 is here. Then again this 20 has to be compared with its children. So now you have 35 and 30. So 35 is greater than 20, so you have to make adjustment. So 35 reaches this position, and now 20 is here. Now again you can compare 35 with 30, so it is fine. So finally, when I is equal to 1, you can stop the process. No need to decrement it further when I reaches 1. Now finally you read the elements of this max tree as root 18, level 1 elements 17, 35. Okay, level 2 level 3 elements, sorry, now 15, 10, 20, 30, and the last level elements 12 to 1. So this is your heapified, this is your max tree with list elements. So this is how heapification happens. Fine. So now we will discuss a program for inserting a element onto the max heap. Okay, then we will wind up. Hope heapification is clear. Now let's discuss a program. This program can concentrate. We will discuss this and we will wind up. So this program is to insert an element onto the max heap. Okay, for this let us assume this is your binary tree. We will take two cases which was already discussed in the previous class. One case where the element is having a value, that is the element which you're going to insert onto this tree has a value lower than this number, so directly you can add. Second condition wherein we will take the value higher than this number. Okay, so what is actually the node position where the element you need to insert on this heap you need to identify. Let's name all the nodes respectively as this way. So initially you will be having total number of elements as 9. So altogether number of elements in the heap is 9. Okay, and this is the program named push. So push program is going to insert a element onto the heap, and let's discuss now the element value is 5. Okay, the element value is 5, and we have observed that the best position to insert 5 is this position itself. So what you have to do first is you have to create a complete binary tree. You have to create a complete binary tree with 10 elements. So when you redesign this structure, left child of this is the node with no child, so this would can you can create one tree, you can create one node as a left child of this node 5 node. Okay, that would be named as 10, node number 10. So that is the node which you need to create, and there whether the inserted element will it reach there or not, that's what we need to discuss. Okay, so now let's come back to this program. So the element is 5 now. Let's assume the element value is 5, and now first we check if heap size is equal to array length minus 1. This situation exists. Suppose if we consider that the heap size is 9 now, total elements in the heap is 9. If it's equal to the capacity of the array, let's assume that we have created an array with 9 elements. So if it matches, then we have to increase the array length to ensure that for the element which is inserted, you have a extra memory. Okay, so this is just to double the array size. So suppose if you are having 9 elements now, capacity is full because already you have 9 elements, 10th element you are stuffing, so it increases the array to 18. So array length will be doubled. Okay, so you can ignore this, no problem. Okay, now let's concentrate on this. So first what we do is we take current node is equal to heap size plus plus. So currently the heap size is 9, now it becomes 10 because 10 elements you will be having now. You make insert stuff, right? So current node is 10. Okay, and after that you enter this loop. Let us see whether do you have to insert. First condition which you are checking is it a root node? How do you address it whether it is a root node? Compare it with 1. Okay, so we will check while current node not equal to 1. So if it's equal to 1, you have to stop the process because you have reached the current you have to reach the root node. Now the current node is 10 and it is not equal to 1, so this statement is true. Then you have this statement, if and heap of current node by 2. So what is current node? 10. What will be 10 by 2? 10 by 2 becomes 5. So is heap of 5 less than the element? Let us see the structure. Heap of 5 is 7. The element present at heap of 5. This is your heap of 5, and it is less than the element. What is the element which you're adding? Let's assume 5 is the element, so you can label it. This is 1, this is heap of 1, this is heap of 2, this is heap of 3, heap of 4, heap of 5, heap of 6, heap of 7, heap of 8, heap of 9, and heap of 10. Okay, so this is a complete binary tree with the 10 elements. Okay, and now, so what we compare is the node position, current node by 2, which is 5. The element is 5, and its position, current node position is 10, and that is compared with the node by 2 position. It's compare it with its parent. So node by 2 position is 5. So at the 5th position the element is 7, and the value 7 is higher. Value 7 is higher than the element, so this condition is false. Is it okay? So heap of 5 is less than the element. Yeah, actually heap of 5 value is 7, and it is no, it is greater, right? So this is 7, and it is actually greater than the element, so it does not enter this while loop. Okay, which means that's the correct position for your current node to insert the element. So what we do is, at heap of current node, what is the value of heap of current node? At heap of 10, put the value, the element. So at heap of 10, this position, heap of 10, put the value 5. That's the best position for the element. So after inserting, 5 goes to the node 10. So this is your label, node number 10. Node number 10, you have 5. So this is what happens when you insert. So this is the case when we have where we have seen a situation where you do not have to move a element down or up. Okay, so directly you can add. Now let's discuss second method, wherein the element which you're going to add is 20, and it has to go to the root, because this is the maximum value which you are having, and it has to be compared with every node value, and finally you say that this is the position for this node to go happens to be the root. Let's see how this 20 goes to this position, one position. Okay, so first we will compare the new element. Now first case, size is 10, so this I'll not talk about. So first, current node position is 10, element is 20 now, and we compare this. While current node not equal to 1, definitely current node is 10, and heap of current node by 2 we check. So heap of 5, is it less than the element? The element value is 20, and heap of 5, what is heap of 5? 7. So 7 element is definitely, value 7 is definitely lower than 20. So it enters the loop. It enters the loop, and it is going to perform this. Heap of current node becomes heap of current node by 2. Okay, so what we do is, you put heap of 10 at the position 10, put the value what is there in 5. Okay, at the position 5, what you have at the position 5, we have a value now 7, right? So 7 goes to 10th position. Is it okay? So it is pulled down. Is it fine? So it is pulled down, so at this position it goes, but here you have the value, you have to update it. Is it okay? So now this is the situation. So current node is changed. So 5th position is empty, 10th position, the earlier 5th position value is stopped. So this is the structure, equivalent structure. Now let's look at the next condition. What happens after this? Make current node is equal to current node by 2. So current node becomes 5 now. Earlier it was 10, now it becomes 5. So when it is 5, again you check 5 is not equal to 1, and then we check this heap of 5 by 2. Heap of 5 by 2, you're checking this node with its parent. So heap of 5 by 2 becomes heap of 2. Heap of 2 value, is it less than the element? We will check. Okay, so what is heap of 2? Heap of 2 value is 8. Okay, heap of 2 value, when we look at, this is the structure, updated structure. Heap of 2 is 8, and element value is 20. So again you have to pull down. So this is actually the place where this 8 can be moved, because here you have now 7 being, so you can update it with this position. Okay, so you have definitely have to move down, so 8 will be moved to this position. Okay, so what happens now? Heap of current node. So heap of current node becomes heap of uh, phi at heap of phi, the value at heap of phi by 2. That is, place the value what you have at heap of phi, what is there at heap of 2. So 8 goes to this position. Don't take this tree, because already we have seen what the structure is. So this 8 goes to this position. Below this you have 7. Is it okay? So 8 reaches here. That structure is this is the equivalent structure. Okay, 8 reaches here. So now you're in current node is fine. Now you have to update the node. Current node should be divided by 2. Okay, so what we do, again we make current node is equal to current node by 2. Now the current node becomes 2. Okay, then again you come back, again you check, while current node not equal to 1, current node is 2, and again we compare heap of current node by 2. Now this does heap of 1, so current node by 2 becomes heap of 1. So heap of 1 value is 9, and that's definitely less than 20 value. So again this 9 has to be pulled down. Okay, so what we do, at heap of current node at the position 2. Now this position is vacant because 8 is pulled down. This position is vacant. At that position, what you have at heap of a node by 2, that is 9, put the value 9 here. Okay, so 9 reaches this position, and this position is vacant now. Here you have 9, but that can be replaced by 25. Okay, so what we do, current node, after inserting current node is made current node by 2, so current node becomes 1 now. Then again go back, while current node not equal to 1. No, this is false, because current node is now actually 1. So come out of the loop, then at the position 1, heap of 1, you insert the value 25. So this way 20 value reaches the node position. Hope the time being this much is fair enough.